Welcome students, we're going over section 12.8. We're doing arc length for a three-dimensional curve, and we're given the definition for this arc length and what we would like to do, and notice it's just a regular distance kind of formula. What we're going to do is, first up, we're going to prove that the circumference of a circle is 2 pi a. Well, we kind of have to understand that r of t, we need to know the equation for a circle, and a circle of radius a would be a cosine t, a sine t. And this will give us a circle of radius a. And this would go for t in between 0 and 2 pi. So let's get the arc length of this. So L is going to equal from 0 to 2 pi, and we're going to need square root of, and my F is that is in the I position, the I component position. So I need its derivative, and then I'm going to square it. So the derivative of this would be negative a sine t, quantity squared, plus, and then that would be a cosine t, quantity squared, dt. And then I'm going to do this computation. I'm going to square it, and hopefully you can see that both of these will have an a, and I'll have a sine squared t and a cosine squared t, so I believe I'm going to have my identity there. Alright, rolling with my computation, I just squared that, factored out the a squared, found my identity, and the square root of 1 was going to be 1, and the square root of a squared is a. That's just a constant. I can pull that out front. So my integral is just going to be t evaluated from 2 pi to 0, and doing that I do get 2 pi a as the circumference. This next one so is to find the length of this cycloid, and notice that I have 4 segments here, all of the same length, so I could just do it, since this goes all the way around the circle from 0 to 2 pi, I could just say that the length here is going to equal 4 times from 0 to pi over 2. That way I can just go just 4 of those segments, and then I will say, whoops, it's right here, and then I have to take the derivative of this. It's going to involve the chain rule. Take the derivative of the outside. That would be 3 cosine squared t times the derivative of the inside, and that would be minus sine t, and then that quantity squared, plus, then I'll take the derivative of the sine cubed t similarly. Alright, I just squared each of these terms and then wrote that down. Notice how I have a 9 in each, so I'm going to be able to pull that. The square root of 9 is a 3, so there's a 3 out front here. I'm going to see what I've got inside of this. I'm going to pull out what I have in common, which would be, looks like I've got a cosine squared in each, and I have a sine squared in each, and then I'm going to write down what I have left. If I pull that, I have a cosine squared t left over, plus I have a sine squared t left over here. And if you'll notice, I have the identity conveniently enough right here, so that's going to be a 1. And this is, each of these is squared independently, so I'll take the square root and then I'll write down what I have. Okay, at this point I could let you equal either the cosine t or the sine t. I think it'll be a little easier to let u equal the sine t, that way I don't have to deal with the negative on the front end. So notice what I did here was du is this cosine t dt, so all I needed to do was just plug in the u for sine t, and that's my du. Now I do need to deal with my limits of integration. When x is 0, or when t is 0, u is 0. That one's easy. When t is pi over 2, then the sign is 1. So my limits will be this, and it looks like I'm going to get 6 as my total answer. For my next problem, I am to calculate how far an eagle travels in 10 minutes if it is rising at a rate of 100 vertical feet per minute, and here is the position vector. So I know that the position vector will give me the magnitude. If I look at this, it will actually give me the speed. So I'm going to be looking at this magnitude of the velocity vector. So let's write down our velocity vector, and that's going to be, I'll write it all down. So here's our velocity vector. If I find the magnitude of this, of course that will give me speed, and if I can find the speed, then notice I can get that length by using this integral right here. So that's what I'm going to do. Alright, doing this computation and using my identity for sine squared t plus cosine squared t is 1, I'll get just a straight up value for the speed of 269. Now I can say that the length of this, evaluated from 0 to 10 minutes, of this 269 is then going to be, dt, is then going to be 2690, because it's 269t, and then put the 10 in. There you go. So it is that many feet in that 10 minutes. Okay, now I'm sitting here with this equation, and there's really not much to do with it except for that within this table here they told me that I can let a constant alpha, which is about 1, be equal to b over a. So I'm going to do that. That way I can factor out an a squared and get one of these constants out of there. Alright, so I'm going to be able to get this a out of here. I'm going to make use of the fact that I have some symmetry and I went all the way around the circle, but I'll just go ahead and say that I have 4 of those lengths, and I'm going to do it from pi over 2 to 0 and just kind of whittling this thing down just a little bit. Now the only ones I can really work this for are the ones where my alpha is 1. Anything else I'm going to have to use the calculator to do some numerical integration. So I'll work this for Venus, and I'll prove this one for Venus first up. So 4 times, and they tell me for Venus my A is 0.723, and then my alpha is 1. That's going to give me a 1 here, which is just going to give, whenever I go to integrate it, that's just going to be a t, so I'll just write down a t. Evaluated from pi over 2 to 0, and then I'm going to crunch those numbers. Alright, this is what I get, and if I go to compare, looks like I've proven it for Venus. I could just as easily prove it for Neptune, plugging in that for my A and then crunching my numbers. For the rest of these bad boys, you're going to have to do numerical integration because you can't do it straightforward. And I'm not going to prove it for all of them, but you could satisfy it within yourself if you'd like. Okay, I'm going to get arc length when given this in terms of a polar curve, and here is my r function, and the arc length is going to be, I've got to figure out my limits of integration are going to be from 0 to 2 pi. My function is just a plain theta, so we'll write that down. Alright, pretty straightforward so far, except for this is still kind of ugly because it's a theta squared plus 1. I'm going to look up my table of integration, and it is quite messy. If you'll go look up in your table of integration, you'll see, you'll get the following. A rather messy looking boy right there, but you know, you're just going to punch all of that in your calculator, and what you're going to end up with something like 21.26. Next, I've got this it kind of looks like a little heart shape, so it's cardioid, and here's my r function. My length is going to go from 0 to 2 pi, but I could make use of symmetry and just do it from 0 to pi and just write a 2 out here, which is what I'd rather do. And then it's going to be the function itself squared, so that's 1 plus cosine theta squared plus the derivative squared, so that's just going to be, the derivative of this is just going to be minus sine theta, quantity squared, d theta. Next what I'll do is multiply this out and do a little computation. Alright, at this point that bad boy is a 1, so you're just going to have 2 plus 2 cosine theta. I'll write that down. At this point I'm going to use this half angle identity right here, so that I will get 2 integral of pi 0 square root of, because I just want it in one chunk and something squared, so that'll be 4 cosine squared theta over 2, and see how nicely that'll come out of that square root, which is what I want. Now that's so much better, and I'll be able to integrate this very nicely. I'll write that down. Alright, I integrated that, and so I'll end up with, when I plug in the pi, I'll end up with the, that'll be a 1, so it'll be 8 minus 0, so it'll just be an 8. And there's the length of that curve. In this next theorem, what we're wanting to do is find arc length as s of t. So we're going to take our r vector and we will, or position vector, we'll take its derivative so we can get the velocity. We'll take the magnitude and we'll be able to get this quantity by integrating over my integral, over my interval a to t. So I'm going to start that process. So here I got my velocity vector. Now I'm going to find the magnitude of this velocity, and I'll write that down. Okay, just using my identity again, it's really nice that it works out that way. And now I'm going to use my equation here, integrating this from 0 to some t, and it's going to be 2 square roots of 5 du, and so this will just be 2 square roots of 5 t when you're finished with it. Alright, so there's my s of t. For the b part, they're just wanting me to take this answer that I just found and get another description or another parameterization of r. So this is going to be r of s, and I will just be putting in this this thing right here for wherever there's a t. No real calculus to that, just chunking that in, and this is what I get. And that's it for that one. And that's it for this section. If you have any questions, see me at the Collaborate. Thank you, and have a great